PhD with Manfred Lindner in Heidelberg a few years ago, and then was postdoc in Italy and Germany until she took a faculty position in Odense. And now at the moment she is Bellini Fellow in Padua and will move to Spain, to Valencia actually, with a Ramon y Cajal fellowship quite soon, probably depending on the pandemic. So Claudia is an expert on discrete symmetries, discrete flavor symmetries, probably the expert in the world. She certainly contributed there with understanding how to break the symmetries to different subgroups in different sectors, and also how to combine flavor symmetries with CP symmetries and what implications it has. So, but today she won't be talking about flavor symmetries, she will be talking about asymmetric dark matter and how to save the matter-antimatter asymmetry. So why delta B at low energies from lepton number violation at low energies with asymmetry. So please.
Okay, first of all, thanks a lot to Michael for the kind introduction, also for the invitation to present the seminar today to you. I hope you're all doing well, and so let's get started. Since Michael says usually I'm working more on flavor symmetries, and that's kind of one of the very few talks there's no flavor symmetry appearing, so it will be mostly very basic and easy, I hope. So let me first start with an outline of the talk. So let's say the first 3 points are just very brief introductions. So just to remind you about the experimental data, about the baryon asymmetry, how there are ideas how this has been generated, a short introduction to asymmetric dark matter, everything at a very simple and basic level, just what is actually needed for this idea and this talk I'm presenting. Then I come to the point that has been made a few years ago in the literature by saying if you have lepton number violation at low energies, it will be that if you generated a baryon asymmetry, lepton asymmetry before at higher scales, and you have sphalerons present, it will be washed out. And so afterwards, I will present our ideas of how to save this generated baryon asymmetry, lepton asymmetry, if you have such low energy lepton number violation. And this is done in our case with the help of asymmetric dark matter. Here it's split into parts where I first just present the general idea and then some examples, so which are kind of models which exist already in the literature, and we were just looking into what happens if we add lepton number violation at low energies. Okay, so let's start with the experimental data. This all of you have seen many times, just to flash again and to remind you, we know very well what the matter content of the universe is, so we have information precisely on the baryon density, on the dark matter density. And what is the most striking here probably is this coincidence which we have, that indeed the dark matter density is just kind of 5 times more than the baryon density. So the next point, what you can ask, so now we were already talking about the baryon density, and then we talked about the baryon asymmetry. So the question you can ask, how is this related? Since I'm not sure how much all of you are familiar with this, I just present you briefly the definitions and the formula to set the stage better. So the baryon density, we just express in a proton mass, the difference between baryons and antibaryons, and usually everything is normalized to the critical density. If you look at the Y delta B, the baryon asymmetry, so this is the difference between the number densities of baryons and antibaryons, but this time normalized to the entropy density, which means you have a direct proportionality between the two, and from this you can calculate what you usually find in the literature, this infamous 8.7-ish 10 to minus 11 for the baryon asymmetry Y delta B. So the next question you can ask, actually, it's there, how has it been generated? Actually, how it has been generated, there are many ideas, but what are the prerequisites for generating it? Usually say the 3 Sakharov conditions, which means you have a violation of the baryon number of C and CP and a departure from thermal equilibrium. The first question you would ask is that possible in the standard model? In principle, yes. With the current data we have, we know it's not, and we won't be able to explain the 10 to minus 10-ish value, but it will be way too small. So people invented a lot of mechanisms, proposed a lot of mechanisms. So if you are interested in these, can refer you to the lectures by Mark Trodden that are kind of oldish now, but still already present a lot of ideas and possible mechanisms to generate the baryon asymmetry. What you see here, actually, there are 2 main classes, baryogenesis, the other class is leptogenesis, where you first generate a lepton asymmetry and then this is transferred to a baryon asymmetry. How this is usually done, so let me also introduce the sphaleron processes, which are not easy objects to understand, but what we mainly need at the moment is, first of all, to know that they are effective at a temperature which is above the electroweak, that they do violate B plus L, but they preserve B minus L. That's very important. And that if you want to think in terms of a particle, you just interpret it as an unstable particle that decays to 12 fermions, where 9 of them are quarks and 3 are leptons. So you see here the up and down quarks, and the 3 leptons are the 3 neutrinos. So that's the only information which we for this talk need about sphalerons. And if you have then a leptogenesis mechanism, what happens would be that you create a lepton asymmetry, and thanks to the sphalerons, part of it is transferred to baryon asymmetry. That's how leptogenesis works, by approaching, by just relying on sphalerons doing this conversion. Okay, so there's yet another ingredient missing to the title. So the next point is, for this reason, asymmetric dark matter, which comes back to the question of the coincidence here, this factor of 5, which is between the dark matter density and the baryon density. So indeed, this asymmetric dark matter is an old idea. It appeared in the 90s already. If you want to read a review on it, there's a very nice review from Ray Volkas and Carlo Petracchi on that, for example, which you can have a look at. For us today, the most important points about asymmetric dark matter I try to list here. So what's the idea behind is that, exactly like baryon number, you have a global quantum number in a dark sector, which can be made up of a few particles. If you want to think in simple terms, you just imagine that this is yet another U1 symmetry. And then what's important is you also talk in the dark sector about particles and antiparticles, which you then distinguish by this new quantum number x, as much like baryons are distinguished from antibaryons. And in order to be able to talk about the baryon asymmetry, as we do, so to talk about an Axis of Symmetry in the dark sector, you claim that either only the particles or only the antiparticles remain in the universe and actually are the dark matter that we see today. Which means one crucial point here, which actually we won't be bothering much about because we are not interested in how this asymmetry is really created, only that it's there, is the question of how to annihilate the symmetric component of this dark matter, anti-dark matter. So for us, important is only that there will be a new quantum number x, there will be particles which are charged under this x, and that the X asymmetry will be directly translating into the dark matter amount. Okay, So there's if you're not yet tired after the first 5 minutes, there's a last ingredient to the talk title. That's the Lepton number violation. So if you think about the standard model, just writing down the renormalizable terms, and you leave aside any non-perturbative effects like the sphalerons, you can say that Lepton number is conserved. However, if you write down the Weinberg operator, so the first dimension 5, so the only dimension 5 operator, which you can indeed write down with standard model fields, you will see that you violate Lepton number by 2 units because there are 2 leptons and on 2 times the Higgs. So why is this very wildly used and people are very familiar with this usually is because neutrinos are, they are Majorana particles, Lepton number is violated by 2 units. So you can say Majorana masses of neutrinos are a sign of this delta L equals to 2. Definitely what is massively searched for in experiments, neutrinos double beta decay is a sign of Lepton number violation in a particular channel, one has to say, because that's only the electron channel. And if you think about the LH3, also there are searches for Lepton number violation in the sense of the same sign dilepton signals. So Lepton number violation is something which is expected to be there. Very often it's expected to be delta L equals to 2 because it's related to the masses of the neutrinos, can possibly be related to the masses of the neutrinos, and anyway we are searching for it a lot. So the question then is, what happens if you put all these things together? So let me first come to the point, what happens if you now say you have Lepton number violation, for example, something which generates neutrinoless double beta decay, which is actually not necessarily related to neutrino masses. In principle could be, but just assume you have an operator which violates Lepton number by 2 units and gives you any kind, or could give you any kind of signal. So the point is, what these people in 2015 made was, so we assume there is a baryon asymmetry or lepton symmetry, somehow generated. You don't care about how actually, you just say it's there, you have generated this, and you have done so above the electric scale, which means at that time sphaleron processes are still in thermal equilibrium, so they violate B plus L, but they preserve B minus L. Until there, you are perfectly fine, and that's what usually you always have in every model with barogenesis and leptogenesis. But now assume you add this new ingredient of lepton number violation, for example, because we have seen such a same sign dilepton signal at the LHC. So, which means you add lepton number violation, which is efficient at the TV scale. So this is something which is an interaction, which is also in thermal equilibrium at the scales where sphalerons are still there. So then the claim of this paper is, or what they've shown is, then forget about the baryon asymmetry or the lepton asymmetry you already generated at higher scales, because this will be completely erased and you will be left with nothing in the end. So you may just guess it from the fact that you have B and L, and if you have one combination conserved, but then there is L which is violated, in the end nothing can remain. But you can also analyze this in terms of chemical potentials to make it in formula more clear, and that's what I would like to do in the next. So we are above the electric scale. So we assume that we have the Yukawa interactions of the standard model, which are all in thermal equilibrium. then we have the sphaleron interactions, so the 12 fermion interactions with 9 quarks and 3 leptons. And since we are above the electric scale, as preserved U1, we have the hypercharge. So how does this translate then in conditions on the chemical potentials? So this is something which is well known, which has been done already in the 90s. So for each interaction which is in thermal equilibrium, like the U-cavas, you will have a corresponding correlation between the chemical potentials of the left-handed quark doublets, of the right-handed down quarks, right-handed up quarks, and the Higgs, as the same for the left-handed lepton doublets and the right-handed charged lepton. Similarly, since we said the sphaleron we imagine as this 12 fermion interaction, also there we have a condition for the chemical potentials being involved, which we have in the end 9 quarks, and we have the 3 leptons. So that's also have to be fulfilled. And finally, for the hypercharge, which is preserved, we have the condition that this is also fulfilled for the chemical potentials. So that's what is also goes under the name of the hypercharge neutrality condition. So these are 5 equations in the end, as you can see, for 6 chemical potentials. So for the 6 different species of particles we have in the standard model. Throughout here, I will keep everything very simple in the sense that I will not distinguish between the generations. So all generations, for example, of quarks, left-handed quarks, they have the same chemical potential. If you want to do a more refined analysis, you could, for example, say you distinguish the 3rd generation simply because it's the heaviest one, and then you would get extra factors. However, this doesn't change anything about the main message and the main results. Since we are above electric scale, also the chemical potentials of the doublet partners are not distinguished from each other. And these are just as comments. So now what we are starting with, so we have the 5 equations, we have 6 variables, very easy, we can solve these 5 equations, so we express the 6 chemical potentials in only one. This is what's usually done. So here you get the simple result for the standard model. Since you probably don't like to do the analysis in chemical potentials, but eventually want to get back to the baryon asymmetry and lepton asymmetry, let me just briefly remind you, if you have done an astroparticle course, or just flash it to you how to correlate this. So if you have a number density in equilibrium, and we are always in thermal equilibrium, that's just this expression. So assume we do this for fermions, since leptons and baryons are fermions for us, and we are actually only interested in the difference between particles and antiparticles. And we would like to know this in the relativistic limit. So in the case when the mass of the species is much smaller than the temperature, and at the same time we assume also that the chemical potential is much smaller than the temperature, then computing the difference between particles and antiparticles, number densities, just leaves you with this proportionality, where I actually assume that the chemical potential of particles and antiparticles is just of the same size with opposite sign. That's something which is well justified as long as you have a pair annihilation being in thermal equilibrium. What you arrive at is, you remember now that the asymmetries, we know that these are just the differences in the number densities between particles and antiparticles divided by the entropy, which means we know that this is proportional to the chemical potential, and so is also this Y delta F. The G star you see here is the number of relativistic degrees of freedom at that temperature. In the standard model, if you're above electric scale, that's something-ish like 100. And also when we discuss models which are beyond the standard model in the sense that they have a dark sector and they have more particles, usually we count this to be like in the standard model, like a factor of 100. So it won't be much different. What you see here, the GF, what you have to take into account, this is the number of degrees of, the internal degrees of freedom of the corresponding particle species you are looking at. Okay, so now we have the desired relation between the chemical potential and what we know better, the asymmetries here. So let's go back then to the chemical potentials, which we would like to relate to the baryon and the lepton asymmetry. So here we would, let me first tell you what is actually Y delta B in terms of the chemical potentials, which means we have to think about just who's carrying baryon number in the standard model. So these are the quark doublets, the right-handed down quarks, the right-handed up quarks. You see the factor of 2 here in front. That's because quarks is a doublet, so we have 2 internal degrees of freedom, while you see also an overall factor of 3, which comes here from 3 generations. So you may think there may be another overall factor of 3 from the 3 colors, but that's eaten up by the fact that the baryon number is normalized to a third. So if you do this for lepton asymmetry, you have just left-handed lepton doublets and the right-handed charged leptons. You end up here with a factor of 2 for the doublet, while you have a factor of 3 overall in comparison to here for the 3 generations. Okay, these are the desired relations between Y delta B and Y delta L and the chemical potentials. Now let's plug in what we found as solutions for the chemical potentials when we fulfill all the 5 conditions. So clearly then also we explain only the asymmetries in terms of one chemical potential which remains, which in turn means that they have to be proportional to each other. And probably you may have seen this relation already in the literature if you have dealt with astroparticle physics. So that's just the baryon asymmetry in terms of the symmetry of B minus L. So what happens then actually, so this is the story in the standard model, and this is the well-known standard model result. So what happens now if we are at the level of the chemical potentials, if we add lepton number violation? So which means the next step to think about lepton number violation in terms of interactions and what is the additional condition on the chemical potentials which arise. If you think about it, we can take as one example, if you wish, the Weinberg operator. Then you would see the additional condition on the chemical potentials is just the 1 of the Higgs plus the 1 of the lepton doublet has to give you 0. If the Weinberg operator was supposed to be in thermal equilibrium. So you may argue that, okay, but you're not interested in the Weinberg operator, but in any other kind of delta L equals to 2 operator, which can contain quarks and whatever you want, all kinds of standard model particles and combinations. If you go through the list of delta L equals to 2 operators, which you find, for example, in the work by Babu and Leung or by Andre de Gueva, so you can do this for all kinds of operators, delta L equals 2 up to dimension 13, using already the existing conditions you have on the chemical potentials, which are due to the UCAVAs of the standard model. You will always find that the additional condition which comes from the delta L equals to 2 operator boils down to mu h plus mu L has to be 0. So it always resembles the one which you can directly derive from the Weinberg operator. So this, however, is another condition. So that's condition number 6 you derive. And this is clearly independent from the conditions which we have here already. So that tells you that now you have 6 independent conditions and you have 6 chemical potentials. So that shows you that all of them have to vanish, which in turn means that also the symmetries have to vanish. So that's just the, how to say, the little computation in terms of chemical potentials, which belongs to the claim by the group of Deppisch et al., saying that, okay, if you have a lepton number violation, some interaction which is violating lepton number by 2 units, and this is in thermal equilibrium at temperatures above the electroweak scale, all your symmetries will be erased that were already existing at that temperature. So now there are some possible ways out. Number 1 is the one which you can think about if you look into something which is related to neutrinos double beta decay. Because you say, okay, if it's only in the electron flavor, then you may be able to kind of hide the lepton number violation and save part of the lepton and baryon asymmetry from this lepton number violation. That's possible, indeed. So I'm not aware of any model where people actually implemented this, but you can think about this, that these kind of interactions are flavor selective, if you wish. And we at the little computations which we have done, we always assumed that all 3 generations are alike, and we didn't distinguish between the 3 generations. Then you can, of course, assume that there's no pre-existing baryon asymmetry at some high scale, which can be washed out and erased through this, because it's only generated at a much lower scale. That's definitely also possible. It's an option to get around this. And then the third way out, that's what we were looking into, is that you add another ingredient, and this is asymmetric dark matter. Maybe. So this was kind of the very longish introduction to settle the stage, explaining the title and the first part. So not sure if you have any questions to this part. Maybe let's ask them now.
Maybe I can ask one question. So that's mu h plus mu L equals to 0. Is that a condition which applies for all possible delta L equals 2 operators, or it's always?
Yes, it's always this one. So it's not. I mean, you may be, if you look at it, you may think that's only the Weinberg operator. No, but any kind of other operator you can write down of the list, or Andre de Gueva's list, you can always boil it down to this, just by using the UCAVAs you already have for the other particles. So for example, if you think about a dimension 11 operator, delta L equals to 2, where you also have quarks, in order to rewrite it in the end in this form, you just have to insert then already the conditions on the chemical potentials which you get from the quark UCAVAs.
Thanks.
Claudia, may I have also a question? So,
Yes.
So you mentioned it's one of the possibilities of different flavors, you know, the distinguishing the interaction. Can you remind us when the interactions which are mediated with the typical Weinberg operator decouples from the thermal equilibrium, what temperatures we are talking about, how high they should be, or when this happens?
I mean, if you talk about the Weinberg operator really, and you think about generating neutrino masses with a Weinberg operator, then it's temperatures like 10 to the 11 GeV. So, I mean, you shouldn't be afraid if I talk now about delta L equals to 2 processes. This is not the Weinberg operator only.
So when they decouple this interaction, I see. So you're talking about some more general stuff.
No, it's completely different. No, be careful. It's not, we are not, so there's no claim about if you generate neutrino masses with a Weinberg operator, which is also delta L equals to 2, and you only generate neutrino masses, your asymmetry will be erased. That's not the case because it's decoupling.
Okay, yeah, so that's what I wondered.
So weakly coupled. No, what it is, it's indeed, you think about more that you have one particular type of new particles giving you interactions which give you neutrino star beta decay, for example. Or these same sign dilepton signals at the LHC. Then you usually have particles which have masses of TeV-ish or so, and these have order 1 interactions.
Okay, clear. Thank you.
Other questions, comments? If not, let me just move on. So I hope the stage is settled. And now the problem is kind of clear. If you add this 6th condition on the chemical potentials, then you lose everything. So you have to now try to cure this by adding some new ingredient. In our case, that's the asymmetric dark matter. So I already had this list of like asymmetric dark matter in a nutshell, what you really need to know about it. Here, let me just remind you about what we actually, for the moment, we need. So we would like to have a new global U1 symmetry. So this U1x, which is so an X quantum number. And what we need, okay, we have at least one dark matter particle, one dark matter candidate, which carries some UX charge. So you can always normalize this to 1 if you wish. If you want, you can normalize it to 1/3 or whatever if you want to have it like baryon number. But that's not important. Also for us, it's actually not really important whether this thing is a scalar or a fermion or it's a fundamental particle or a composite. It's just there. So now, in the following, this will be completely general discussion in the sense that we will just go back to the relation between the asymmetries, which we just derived together in the standard model. So baryon asymmetry is related with this factor to the symmetry of B minus L. Then you can ask yourself in very general grounds, what changes if I have yet another asymmetry? Now I have this X asymmetry and I can associate this Y delta X to it. Then what you would expect, very naively, without having any model in mind, is that this relation gets modified. So you will have, of course, this new term with this A2, where also now this is a correlation between the 3 different asymmetries. If the A2 is 0, you're back to the standard model. Let's avoid this. In the following, one thing I also would like to avoid is that this coefficient A1 here is equal to 1, because if that's equal to 1 indeed, you will see that the baryon asymmetry drops out and you will get a direct proportionality between the lepton asymmetry and the Axis symmetry, which would be, let's say, a miserable coincidence. And however, in all the models we looked at, it didn't happen. So it would be just, it's a very particular point you can hit. So that's just a claim. For the moment, this is just a claim. I have not shown you any model or anything which can actually realize this, but this is kind of a logic argument. That's what happens if you add another sector and you have another symmetry to play with. So, however, you can ask yourself, what can I do with this equation? What can I do? I can, first of all, I can rewrite it with the densities if I don't like the asymmetry so much. So I write it with the omegas, and that already looks a bit better and a bit closer to data if you wish. And now in the next step, I can also say, like, now I actually have this omega chi here, which is the density of these chi particles, which should be our dark matter. Now, let's assume, so what it always should be, this density should be less than the dark matter density, which is actually observed. So if this is given, what happens to this equation here? So you get an inequality, so you get an upper bound. Actually, you can rewrite this as an upper bound for the dark matter particle mass. You have to live with that these coefficients A2 and A1 appearing still there. But still, if you look at this equation is kind of, or this inequality is kind of nice, because you know what the proton mass is, you know what the dark matter density is, the baryon density is, the Y delta B you also know, this is 8.7 times 10 to minus 11. So indeed, in this inequality, you have kind of two free parameters. One is A1 times the asymmetry in B minus L, and the other one is the dark matter mass divided by this A2, or the absolute value of A2, if you wish. If you worry about what A1 and A2 could be, take it to be as order 1 numbers for the moment. So what I want to do, however, is now let's try to inspect this equation or this inequality a bit better by making a plot, which you can do with the vertical axis. Now this is, so to say, the rescaled asymmetry in B minus L, and this is the rescaled dark matter mass rescaled with this factor A2. And so I told you already the Y delta B we know, so that's something we already plugged in here by making this little plot. So in the entire plane, the baryon asymmetry is agreeing with the experimental observations. So what do you see then here? You see that everything which is orange, the density of our dark matter is smaller than the observed dark matter density. While in the gray area, it would actually fit it at the 3 sigma level. And if you're in the white area, you have generated too much of it, and that's not allowed. So what you see then here, actually now you look at the scale of the dark matter mass. So take this A2 as order 1 number. Then you see something which people who are familiar with asymmetric dark matter would expect is, usually you would expect that the dark matter candidate should be sort of 5 GeV. So dark matter, asymmetric dark matter is usually in the ballpark of a few GeV, maybe up to 50-ish GeV or so. You see also the other option, there's not, if you look at the portion of the parameter space, not very likely, but for asymmetric dark matter in general, there's also the option that it can be around TeV-ish. That's what you see in this funnel here. That's also still allowed. So, however, you see actually what you expect in the sense that you have a plane where you have some parameter space which is allowed. So now, why is this a plane? It's a plane because you have added one new degree of freedom, which is the axis of symmetry. Now you can make some observation which is actually funny. Namely, you can make the observation that you have a strip here where the B minus L asymmetry vanishes. So where B minus L is conserved, and still you generate the baryon asymmetry. If you work more on that, that may ring a bell. This was something which was brought up by Stephen Barr already in the beginning of the 90s, and there you actually used asymmetric dark matter for showing that for having a baryon asymmetry, you don't need necessarily to have E minus L violation. So that was another point of him, which is also reflected in this plot here, but so to say only as a side effect, if you wish. So, however, we would like to move on with the question, what happens if we add our lepton number violation, so the delta L equals to 2 processes which are in thermal equilibrium at the TeV scale. So if we go back to the chemical potentials, this means just we have this equation number 6 on the chemical potentials.
I want to bring in my afternoon.
So what would you expect then if you just look at the asymmetries? If you just look at the asymmetries, you expect that with another constraint, you get another correlation. So here, just in generality, we take as correlation that the lepton asymmetry should be correlated to the axis symmetry. Just in order to add a new parameter, which we call A3, which should reflect that there's this additional constraint. So now the question is, what happens to the figure? You have seen this one. You can imagine you add just another constraint, so the plane is not a plane anymore. Indeed, it becomes just a line. So you just collapse one dimension of it. So now, just to make the plot easier, we have chosen some numbers for this A1, A2, and A3, which you see here, which actually correspond to an existing model which people have worked out. So now what you learn from this plot is, okay, at the moment when you add lepton number violating processes delta L equals to 2 that are efficient at the TeV scale, so you can still explain, if you want, the baryon asymmetry of the universe, which was always fine in the entire plane. You, however, have a much more restricted range of masses of the dark matter, which is allowed. Namely, if you want to explain the entire amount of dark matter which we observe with a dark matter particle which we have proclaimed, then it should be 0.44 GeV. If you want to have less dark matter because you think there may be another component, then the mass should just be less. So, which means what happens in such an asymmetric dark matter scenario, your expectation is you add this lepton number violation, you reduce the allowed parameter space drastically, you practically fix the mass of the dark matter, but otherwise it's still fine. And indeed, it's not telling you that all the asymmetries should vanish, because now you have another sector where you have another symmetry. So you can go back to the idea by Stephen Barr that I was telling you. Could you have now still baryon asymmetry existing and B minus L conserved? No, now then you would ask too much. So indeed, the line here of the symmetry being 0 is now ruled out. So the symmetry in B minus L is also fixed by fixing that you have another condition to satisfy that comes from the lepton number violation at the TeV scale. Okay, so this was the general part and the general idea, and so to say, to show you in very general what happens if you have this dark sector, and if you also add the delta equals to 2. You may argue that this was kind of too general, and that's kind of could also be like that you make up something which actually is not realized in any kind of model and never happens. So make things more concrete in the sense that you study existing models and see what happens in existing models of asymmetric dark matter, whether you indeed find that this happens and that you can compute what A1, A2, and A3 is. That's what we did in the next step. So in the next step, we were back to the general consideration of just, we were searching for models which have this global U1 symmetry, and then there's at least one dark matter candidate. It turns out in order to do these computations and in order to get around all the conditions is we usually add 2 particle species and not only 1. So which means we add 2 chemical potentials through the dark sector. And then we observe that there are a few more things which have to be fulfilled in order to make things work. So that's what you expect. Most of the particles in the dark sector which have this U1X charge, so contributing to this X of symmetry in the end. Only one of them will be the dark matter usually. You will usually have that, what you probably not have seen in our general consideration with the asymmetry, is that if you go back now to the equations with the chemical potentials, usually what you need is that at least one of the new chemical potentials contributes to one of the equations. So to the Yukawas, we don't do anything. The Yukawas of the standard model are the Yukawas of the standard model. So what you can actually change of the 5 equations of the chemical potentials in the standard model is either you change the hypercharge neutrality condition and or you change the electric sphalerons. So that depends on the particles which you add in your dark sector, which tells you that always there will be at least one which has hypercharge and or there will be particles which also have SU2 left quantum numbers and are fermions, so that they are appearing in the electric sphaleron. So that's the crucial point of the entire construction. And that's, however, if you think about it and if you imagine these dark sector models, that's what usually happens. Then the dark matter candidate for us will be always colorless and neutral. So this is kind of a standard dark matter candidate. And this is kind of the last condition is, how to say, is the simplifying condition, if you wish, and that is a condition which easily may not be fulfilled in particular models, namely that all interactions are always in thermal equilibrium. So that all of the interactions which I write down, may it be interactions between the dark sector and the standard model, or may it be interactions in the dark sector only, that they indeed give me a constraint on the chemical potentials. If you look into many models which are more or less sophisticated, which have a dark sector and have asymmetric dark matter or have some sort of cogenesis mechanism where you generate dark matter symmetry and baryon symmetry at the same time, they may easily violate this last condition. Just to say this is a way of getting around some of the constraints. However, for simplicity and easiness, we just include this and we don't distinguish any interactions in the sense that they have been already switched off or became inefficient, but we take them all into account so that they give new constraints on the chemical potentials. Okay, so now the aim, as to say, was you have to modify at least one of the 5 equations which you get already on the chemical potential in the standard model. And the final goal is, in the end, if you count all equations, it's a very simple argument. If you count all the equations in the end, with all new constraints which you get, you would like to add more chemical potentials than constraints. because only in that case you are fine and you have one more handle in order to survive the additional constraint you impose if you take into account the Lepton number violation by 2 units. Okay, so let me just, both of these examples are very brief. Let me just show you the most minimal one you can think of is, actually it's not really a model because this maybe is, let's say this may be sort of like a subsector of a full model, but this is so simple and it contains so few new particles that it's just for showcasing that you can actually write something which is sort of proto-model down to compute what this A1, A2, and A3 are. So the most naive thing you can think about, which can satisfy the conditions which I've just told you, is that you have a sort of mini dark sector where you have vector-like fermions, which have charge +1 under your new global U1 symmetry, and you have complex scalars that have the opposite charge. So you can have many of these, and again, we are very simple in the sense that we say, we assume that all of the fermions among each other mix, and all of the scalars among each other do. So we actually describe all of the fermions only with one chemical potential and all of the scalars only with one chemical potential. So, which is the minimum you can do. So you add 2 chemical potentials for the 2 new particle species, and now you be as minimal as possible is that only one of them carries non-zero hypercharge. So there are 2 variants of this proto model where either the fermions do have the non-zero hypercharge or the scalars do. If only one of them has, you can write down this interaction. And then there's only one interaction at the renormalizable level, namely only with the right-handed charge leptons. All the rest requires that these things would have additional quantum numbers. So the most minimal thing is that you couple it only to the right-handed charge leptons. So now what happens with this mini setup? You do 2 things. First of all, you add some contribution to the hypercharge neutrality condition because one of these species has hypercharge, so either fermion or the scalar, so there's a new term appearing there. That was one of our aims to modify one of the conditions which are already existing in the standard model. And of course, these things have some interaction. So with the standard model, so which means you add this one condition for the coupling to the standard model. Okay, so that's it, which means we have add 2 chemical potentials, but there's only one genuine new equation which we have added, which means we have gained one variable, if you wish, one free parameter. So if you now ask me what is the Axis of Symmetry in this little proto model, this you can just express in the 2 new chemical potentials. And now you have everything at your disposal, and you can compute yourself what A1, A2, and A3 should be. And these are actually the numbers for which I've shown you the plot before. If you want to do this more sophisticatedly, you can think about more generations of these particles, or these particles that have different X charges, not just ±1, and you can take their masses into account. So because this equation here is only valid for the masses being much smaller than the temperature. So these are all kind of variations of what you can do, but the essence remains the same, is that you indeed, so to say, you have written down the most, kind of, I would say this is the most minimal model which you can imagine to fulfill all these constraints which I've set out and which actually give you what I have argued only in terms of the asymmetries without having any kind of model. Okay, in maybe the last 5 minutes, I just show you something which is, if you want, a real model and which has been considered before, but have been written down by other people and has been worked out. So these are simple models where you actually operate either with a generalized Lepton number or a generalized baryon number, which means you have a dark sector which also has Lepton number or baryon number. If you think about the one with the Lepton number, this is an old model by Steve Barr. This is actually the model where he proved that you can have baryon asymmetry non-zero while you have B minus L conserved. And the other one is a model from these two guys here where they gauge baryon number. So the funny point is that although these models seem to be rather different, the particle content is nearly the same. So actually what you see in the following is kind of holding for both of these models, and probably also for more models of this kind, which we have not looked into. But here you add 6 new species of fermions. So they are the vector-like ones, the psi, L psi r. So these have now also quantum numbers on the SU2, which means these ones now also appear in the sphaleron. If we now talk about a sphaleron in this model, this sphaleron also knows about the psi L and psi r. Then you add, so to say, right-handed-ish, so these ethers, and you add the chi's, which are the dark matter candidates in the end, either one or the other, or if there's a Dirac, then this is just the sum of the two. What else to say is usually all of them have the same X charge in this particular model. So the X1 is equal to minus X2 is 1, so that's very easy. So all of them have the same X charge. Sorry. You forget about the Lepton number, which I've told you, because this model only has baryon number. And this particular model has two parameters which are describing these gauge baryon numbers. So this is B1 and B2, while it actually fixes the difference between the two and keeps the other parameter free. That's a peculiarity of the model that has been set up by the guys, so it's not really very important. One thing, what they do, actually, they break the gauge baryon number spontaneously. I mean, then you add yet another particle, so you have 7 new chemical potentials, 6 from the fermions, and then you have 1 new scalar, which just has the purpose of breaking this gauge baryon number spontaneously. You see, it doesn't have, that's important, here these zeros, it doesn't have in particular this X charge, so it doesn't break the X charge. The X charge is always conserved, so we still can talk about an Axis of Symmetry in the end. So what can we do with this kind of model? So first of all, just what I announced before, since the psi L and psi r, they have SU2 quantum numbers and are fermions. So your sphaleron now actually is also having psi M, psi r. The second thing which kind of always happens as a side effect, if you modify the sphaleron, you usually also introduce particles which have hypercharge, which means you also modify the hypercharge condition. So you modify 2 out of the 5 standard model equations for the chemical potentials. But then the next step to do in this issue is, if you want to study the model, you define what the Axis of Symmetry is. So you just look at the particles which have the X charge. You can write this down. And now here, since I said these guys actually consider not only a generalized version of baryon number, but also a gauged version of baryon number, which means you actually add yet another condition on the chemical potentials, because since it's a gauged symmetry, gauged U1, so you have to take into account also like a gauged baryon number neutrality condition in complete analogy to the hypercharge condition. So you also write this one down. And in the end, you look at all Yukawa type interactions, which you can write down for the dark sector, on the dark sector and the Higgs. So we get these bunches of equations. Now, this may be the moment where you start to get worried because we add 7 chemical potentials, but already here you see 7 equations, and you may be worried that we add, let's say, more constraints than chemical potentials to our model. If you inspect them more carefully, you see that not all of them are linearly independent, so don't worry. So in the end, we add 1 independent constraint less than number of new chemical potentials. So everything is fine and things work. And you can still go on and now compute what A1, A2, and A3 is. And if you do that, you end up with these numbers, which you see here in red for this gauged baryon number. So what is common to all of the models, so the first line is what we have looked at in the form of a plot. And that's the minimalistic model, proto-model, which only modifies hypercharge. The other one is the one with the gauged baryon number, but also the ones which I've not talked about. They have all in common that this is the mass of the dark matter which it should have in order to explain the entire dark matter observed. And at the same time, you would like to have Lepton number violation delta L equals to 2 processes efficient at 1 TeV. So you see, all of them are confined to have very low mass. So between the smallest is like just half a GeV up to like 6-7 GeV. Okay, so you may worry now, what are the other models? This one actually I implicitly talked about. This is the one with the generalized Lepton number. If you want to know a bit more about the other two, you can. So here are the references for it. Why including these models and why are these interesting? Just as a, I mean, now you read Technicolor and you think maybe, oh my God, Technicolor, and you may not like this. The point about these models is that indeed this one here, the model by Barr, Civukula, and Fari was kind of the first model to have asymmetric dark matter, and these kind of Technicolor models with a new strong gauge group, Technicolor group, are sort of kind of the ideal world where you say this is the most natural place where I think that I can have sort of a new type of baryons, technibaryons, which are like mass 5 GeV-ish. So they are kind of the ideal playground for the asymmetric dark matter idea, where you have then a technibaryon number for this sector. And these are just 2 variants. So this is kind of the original model where the strong group is an SU4 and this is called ultra minimal Technicolor. This is like kind of a more modern version where due to a different particle content in this Technicolor sector, you can have an SU2 strong group and just instead of an SU4 one. Okay, all these models of this type you're well aware of are not that great anymore, confronting the data that we have about the Higgs. So if you want to make them variable, you actually sort of should extend them more or less with an elementary Higgs particle to satisfy all the data which we now have, in particular on Higgs and electroweak physics. In that sense, these are probably not the most fancy models you would like to look at, but still they are kind of where the kind of the prime candidates for asymmetric dark matter to have. Okay, so I think that would be it, in the sense that just after all what I did, to remind you, the caveats of this analysis and what we actually were looking at is really that you can easily invalidate also our arguments by saying that you have some sophisticated model where not only interactions are in some equilibrium at like TV also. You can easily say like, anyway, I don't care about lepton number violation efficient at the TV scale because I generate the baryon asymmetry below the electric scale. That's also fine, you could. And of course, what we assumed to make this work is that the dark sector, which has the asymmetric dark matter, is interacting in some efficient way with the standard model, may it be through the sphaleron, may it be through some interactions. If you decouple it way before, it can't do anything for you. And you will still suffer from the lepton number violation to wash out your preexisting baryon symmetry. Okay, so then let me just flash the main messages, take-home messages, what we were looking at, but you can read that. And otherwise, I would say thanks a lot for listening to the talk. And if you have questions, please ask.
Thank you very much, Claudia, for a very nice talk. Do we have questions? Who wants to start? Let me start with one. So, so you showed that the masses are typically very light in those models. Did you think about what a model would have to satisfy to have a larger mass or to have a...
That's kind of...
So the Technicolor models, they always have the largest masses, or they have the largest masses among those.
No, not necessarily. I mean, just look at this plot here. Just go back to the very general considerations. I mean, this is the plane which is allowed as long as you don't add lepton number violation delta L equals to 2 interactions. So if you now, and this is the effect when you add them. So you cut out one dimension of the plane. So depending on what A1, A2, and A3 is the cutting out happens at different horizontal levels, if you wish. So you see, before you have anyway just this funnel, which allows you to get to higher masses for the dark matter. If you manage to arrange the A1, A2, and A3 in such a way that you hit the funnel after cutting out, you're fine. We have not seen, I mean, that's a fine, in the sense it's a fine-tuned case if you look at this plot. However, you can have the most natural model you think about that has the right particle content such that in particular this A3 has the right value to end up exactly here.
Okay.
You see
but
what I
if
mean?
one looks at it naturally, it looks like it's always, or it prefers kind of low masses.
Yes. That goes very well with the fact that anyway asymmetric dark matter likes lower masses. So I mean that's what people most naturally would say. Asymmetric dark matter is something with some new kind of baryons which are 5 GeV, 5 times heavier than the proton.
Exactly, but one would have expected something kind of that.
Yeah. Yes.
Naively at least. Thanks. Are there other questions? Ah, wait, there's Bruce is raising his hand.
Claudia, thank you for the talk. Can you just go back to the point where you introduced the A3 parameter?
Yes.
It was maybe about the halfway mark.
The A3 parameter. Let me see. I do this one. We had now. So we go on here. Yes.
Yeah. So it wasn't clear to me whether that was a choice that you can make without loss of generality, or whether there are other assumptions getting buried in that choice, being included via that choice. Do you want to speak to that?
Yes, of course. The very fact that now the lepton asymmetry should be in this way proportional to the axisymmetry, this is a pure choice.
Okay.
The generic answer is before you had just one correlation between the three asymmetries.
Yep.
You just get, through having another constraint, you get another correlation, which is independent of the one before. So that's the only constraint you have. And if you don't like to have this relation between lepton asymmetry and axisymmetry, you could also write the equivalent equation right down between baryon asymmetry and axisymmetry. That's perfectly fine. It has been our choice to define the A3 in such a way.
Right, but I'm less concerned about, I mean, clearly you can reparameterize this in some, in some way. I guess my question is about the substance of the constraint. I mean, are there scenarios where instead of the constraint, the new constraint reducing the funnel into a line segment, can it turn it into a curve or a loop or something not simply connected? Or can it turn it into a Cantor dust of isolated
I see. Yeah,
points?
no, I see. So how you plot it in the end, whether this is a line or this is a curve, I think it depends on the parameters. So the only important point is that before you had, before you had one equation between three independent asymmetries. While with adding this new constraint, you have one more equation which these three asymmetries have to fulfill. So that's easiest to see, that from having a plane, you reduce to a line. So you just lose one dimension in it.
So you've chosen a particular example. So I guess then my question is that you have, I think it's 4 or maybe 5 substantial, 4 or 5 actual examples towards the end of the talk.
Yeah.
Are all of those, is the extra constraint in all of those truly expressible via an A3 parameter in each of those cases, or is this just the nearest guess to an A3 parameter?
The numbers you see here, they are exact.
Those are exact.
Yeah.
Okay, so that it produces a linear relationship of that kind is at least representative of these 5 cases.
That's natural, because if you think about all the equations which I've written down, the constraints on the chemical potentials, they are always linear in the chemical potentials. Then the asymmetries, the Y's, they are always proportional, at least in the approximation which I've used, high temperature, relativistic case. The Y's are always directly proportional to the mu's. So there's actually nothing more which you can expect than a linear relation, and something which you can examine false. Does this answer the question?
That answers my question quite fully. Thank you very much.
Okay, so I think in the interest of time, since we are past 5 o'clock, I say we thank Claudia again for a very nice talk. And I'm sure she's happy to answer more questions afterwards.
Of course.
But nobody should feel obliged to stay, or if they have to leave, they can leave also. So thank you very much, Claudia.
Thanks to you for listening.